You ever watch a perfectly healthy production environment just spontaneously fall over? You know the feeling. You're checking the dashboards, traffic looks completely normal, your database is happily responding, but for some reason, your API is just completely dead. Well, welcome to this explainer. Today, we're adopting a senior engineering mindset to really dissect the hidden complexities of distributed messaging systems. We're going to look at RabbitMQ, system resilience, and honestly, the underlying architectural secrets that separate a senior developer from the rest of the pack. Let's get right into it. Okay, so let's dive into this total nightmare scenario. Imagine a catastrophic hot pod failure in production. You've got this perfectly balanced layer 7 mesh, right? Traffic is flowing exactly as designed, but suddenly, out of nowhere, one single pod becomes a hot pod. You go check the logs, and it's not some massive flood of traffic. Nope. Instead, it's literally a single, massive list user's API call that takes 30 seconds to execute. It eats up 100% of the CPU, and it completely ignores your perfectly balanced mesh. Section 1. The synchronous death trap. Dealing with this demands a massive mindset shift. See, a junior developer spots a random 100% CPU spike, watches the system auto-recover, and just logs it as a transient error. We've all been there. But senior developers, they know that just waving away a failure like this is incredibly dangerous. Physics always wins. If you can't explicitly explain why the error happened and exactly why it stopped, you haven't actually found the root cause. You've only found a coincidence. You absolutely have to track down the actual bottleneck. Here's the thing you have to realize. When a single request crushes a pod, no amount of traditional load balancing is going to save your system. Think about it. Your load balancer actually thinks it's doing a stellar job because the number of requests is perfectly distributed. But because that one single request is disproportionately heavy, the pod locks up computing data. This isn't a network scale problem. It's a compute problem. So subsequent requests get routed to that pod, and they just pile up behind the blocked thread until, boom, the whole thing times out. Moving on to Section 2, Job Queues to the Rescue. There is a really fundamental difference in how you approach a heavy request. The junior, kind of tutorial-driven approach is to just wait synchronously for the HTTP response. The client clicks a button, the server grinds away for 30 seconds, and the connection just stays open, entirely blocking critical threads. But the senior production reality? You return an HTTP 202 accepted instantly. You acknowledge the request, hand them a job ID, and basically offload all that heavy lifting to RabbitMQ. And here is how this builds perfectly into the work stealing or job queue pattern. First, your API gets that heavy request. Second, instead of actually processing it right then and there, it publishes a job to a broker, like RabbitMQ or SQS. Third, it instantly returns that 202 accepted with a job ID. Fourth, a background worker, which is pulling from RabbitMQ, processes the job asynchronously entirely at its own pace. And finally, the client simply pulls the server or waits for a webhook. By implementing this flow, you completely decouple the immediate web request from the heavy processing. It's like wrapping your API layer in a bulletproof vest against CPU exhaustion. Which brings us to Section 3, the exactly once delivery myth. So moving to RabbitMQ introduces this really dangerous myth, the idea of exactly once processing. Systems like SQS, RabbitMQ, and Kafka, they prioritize availability. That means they provide at least once delivery. Let's be real. Network failures are inevitable. A request might actually succeed on the server, but the acknowledgement gets dropped, which naturally causes the system to retry. Automatic retry logic in API gateways and load balancers means your consumer will absolutely 100% see duplicate messages. It's a guarantee. And this brings us to a completely non-negotiable concept in distributed systems, idempotency. Think of the classic Uber double charge scenario, right? A user taps Pay Now, their cell network hiccups, the request times out, and they frantically tap Pay Now again. Without idempotency, they get charged twice, and at scale, this happens thousands of times a day. Idempotency simply ensures that no matter how many times that duplicate message hits your consumer, the end result does not change beyond that very first application. Senior engineers know to watch out for these common red flags. A massive mistake is implementing idempotency at the API layer, but totally forgetting about the message consumers actually pulling from RabbitMQ. Another big one? Failing to implement a time to live, or TTL, for those idempotency keys, which just leads to totally unbounded database storage bloat. And honestly, the worst of all, making operations idempotent simply by swallowing and ignoring errors instead of safely handling them. You have to enforce idempotency by checking deduplication tables before your worker processes that RabbitMQ message. Section 4. Surviving with back pressure. Now, handling duplicates is only half the battle. You also have to survive when the system is just completely overwhelmed. Ever lived through a retry storm? It's basically a manifestation of the butterfly effect in distributed computing. A localized failure happens, say your database blips for just a second, the client retries. Then downstream clients of that client start retrying. Because everyone is retrying at the exact same time, traffic grows exponentially. What was just a momentary little blip turns into a massive, self-inflicted denial of service attack that completely cripples foundational components like your message queue. And this is exactly why we desperately need back pressure. When your RabbitMQ consumers are under extreme load, they have to be able to communicate this back to the producers. Implementing back pressure, like actually waiting for consumer acknowledgments before firing off more messages or setting really strict concurrency limits, is quite literally the only way to prevent buffer overflows and cascading failures. If you don't tell the producer to, hey, slow down, your queues overflow and your entire system dies. Section 5. Mastering the outbox pattern. Okay, now we have to tackle arguably the most insidious backend problem out there, the dual write. Imagine this scenario. You have a microservice that saves a new user to your primary database, and then it publishes a user-created event to RabbitMQ, so other services can, send out a welcome email. But what happens if the database commits perfectly, but the network drops right before you publish to RabbitMQ? Well, your database has the user, but the rest of your system has absolutely no idea they exist. You can never guarantee that two separate distributed systems will commit simultaneously. Your system is now permanently inconsistent. Which brings us to the outbox pattern. This is how you solve the dual rate problem forever. Step 1 and Step 2 happen inside the exact same database transaction. You save the business entity, and you save the event payload to a dedicated outbox table. Because it's a single relational transaction, it either fully succeeds or fully rolls back. Simple as that. Then, a separate background processor reads that outbox table, publishes the message to RabbitMQ, and marks it as processed. By doing this, you guarantee that the intent to publish is never, ever lost. Now, for the real senior engineers dealing with massive high volume, how do you actually scale that outbox processor without your threads constantly stepping all over each other? You use database locking mechanisms. Specifically, select for update skip locked. This brilliant little trick allows multiple background workers to claim entire batches of rows from the outbox table in parallel, completely skipping the rows that other workers are already locking. It's a high-performance database trick that lets you process thousands of messages a second safely. Finally, Section 6. Delete code, build resilience. Ultimately, mastering these patterns really allows you to step back and rethink your actual value as a developer. Consider this staggering stat. 96% of developers do not fully trust AI-generated code to be functionally correct in complex systems. And honestly, they're completely right to be skeptical. LLMs don't fail loudly. They return this really confident-looking output that is just semantically wrong. Deep human understanding of these distributed edge cases, things like exactly once delivery myths, retry storms, the dual write problem, it's irreplaceable. You simply can't auto-generate an outbox pattern without actually understanding why it's there in the first place. Think about the true developer's journey. A junior developer's contribution graph often looks like mountain peaks. They're super busy adding thousands of lines of code, bolting on new features, writing endless try-catch blocks. But a senior developer's graph, it looks like a valley. They systematically delete entire redundant microservices, they drop unused dependencies, and they remove features. They create these beautiful valleys of stability. Because ultimately, the best code is the code that literally doesn't exist. By shifting your synchronous burdens to RabbitMQ, actively enforcing idempotency across all your consumers, and applying that outbox pattern to guarantee data consistency, you're actively removing the complex, brittle code that tries to manually juggle all these failures. You're letting the architecture do the heavy lifting instead of relying on a giant block of application code. So I'll leave you with this question to chew on. As you walk away from this explainer, I want you to audit your own system. Go find that single, heavy, synchronous request that's holding everything else back. Is it a massive database query? Is it a terribly slow third-party API call? Find it, tear it down, and offload it to a job queue. Build systems that embrace failure rather than just pretending it won't happen. Thanks so much for joining me on this deep dive.